for the effect of degradation on the elastic modulus, on the loss modulus, we found that it is systematically decreased. So here this is a degradation time dependence of the elastic modulus is decreased linearly, and the glass transition temperature also decreased, but for the polylactite it is still stay the same. There is no any change. And we have also done some rheology, melt rheology, to study the viscosity of the material with degradation time. So the material, the viscosity, the complex viscosity decrease systematically with increasing degradation time. And this experimental data can be fit well with Caro model, and then we can calculate also the zero shear viscosity as a function of degradation time. And this is an inset plot, show that the zero shear viscosity decreased linearly with increasing the degradation time. And this is most likely because we got a very small molecular weight with very low viscosity. And this is also very different from polylactite. So this is a DCC measurement. This is the melting point. So the melting point is a little bit shifted to lower temperature, and the magnitude of the melting peak is decreased dramatically. And then by measuring the enthalpy of flow as a function of degradation time, it decreased exponentially. And this proved that the degradation is not only takes place on the amorphous, but also on the crystalline part. It is totally different from polylactite, and this is the crystallization behavior. So it is shifted to lower temperature, which means that the material becomes more, let's say the crystallization decrease also. And I proved that by doing some rheology. So what I have done here, I start from the melt, so the material is in the melt, and then I decrease the temperature by a constant cooling rate, and they measure the elastic and the viscous modulus of the material. And the crossover point is due to the material changes from totally amorphous to the crystalline. So it's like it changed from like a liquid-like behavior to solid-like behavior due to the crystallization. And then you can calculate, just the crossover point, it is either gelation temperature or crystallization temperature. And then you can do that for different material at different degradation time. So you calculate the inflection or the crossover point at different degradation time. We found that the gelation temperature is decreased linearly with increasing the degradation time. And this is also proof that the degradation of polylactite takes place on the crystalline and amorphous part. Polyamide, it is bio-based. We can get the tall oil from pine tree. And through unsaturation fatty acid, we can make the dimerization to get dimer fatty acid. And through the polycondensation, we get the polyamide. The polyamide is normally used as bio-based polymer binder in ink industry. So this material is very elastic, and it is not degradable. So the only problem about polyamide, it is a little bit expensive. By mixing polyamide with lignin, we can reduce the cost. And the good things here, by mixing the material up to 30% lignin, we still have a very good mechanical properties. Even the mechanical properties increase a little bit. And the glass transition temperature is still remaining the same. So, and this is the Young modulus, it is increased with increasing the lignin content. And the material looks very nice. So this is a way that we can use, still we can use polyamide, even it is very expensive, but by mix the polyamide with lignin, so we can reduce the cost very significantly.
Do you get rid of the terpenes in that process? Are the terpenes reduced in that process of conversion from pine pitch to polyamide? Is it the terpenes released?
Terpene released?
Terpenes, are they released in that situation?
I don't think so.
Because if it is, you might also have one other factor going for it, which might be resistant. It's a natural repellent in some cases. You have terpenes still involved in that in some situations. Pine pitch is a natural insecticide in some situations.
That might, if you stretch it, explain what you saw with the roots.
Well, that's a question mark I'm asking. Are we seeing some things there that we wouldn't otherwise? And it's just when we look at a lot of this stuff coming out of these natural-based plant products, you're going to have some other side factors we're going to have to watch real carefully. But be interesting to find out.
Okay. Okay, so this is for polylactide and lignin. So it is already used for even for higher concentration. We have checked this composite up to about 50%, and the material was nice. Here, this is some of the commercially available pot. They are very good pot, but the problem is they have very poor mechanical properties and very high water sensitivity. And this is why we thought about the polyurethane coating. This is bio-based aqueous polyurethane coating. It is outstanding adhesion. It has a lot of advantage using polyurethane dispersion. It has outstanding adhesion to a lot of synthetic material, wide range of flexibility combined with toughness, high chemical resistance, resistance to discoloration, excellent weatherability, and we use aqueous dispersion. So this is why it is highly, it is good for health and environmental safety. So because it used to reduce the organic volatile solvent to the atmosphere.
So you can paint it easily too, correct? I'm assuming you can paint it easily too. Because one of the comments that's going to come out, you see every pot that's painted right now. All the plants out there are colored. This will accept color, right?
So we can, yeah. This is this polyurethane dispersion we use it as a coating material.
Right.
So we can put a color on the polyurethane, and then
I'm asking because that's
yeah,
one of the questions that's out here is pot color.
we can put the color through the coating or just in the injection molding probably, or the processing. So yeah, during the processing we can add the color also, I think. And how we made the polyurethane dispersion is a reaction between diisocyanate with dimethyl propionic acid and the castor oil. Here we use the castor oil, and I will mention why castor oil especially, and then we can neutralize the dimethyl propionic acid to get the polyurethane dispersion, and we can apply it for a lot of substrate. And for our main objective, we use it for the commercially available pot. And this is a castor oil. Naturally, castor oil, it is the only exception from all of the plant oil which has OH group. All of the other plant oil does not have this OH group, and we have to do a lot of chemistry to convert the plant oil to polyol. So, and this costs a lot of money. So I think that one of the question is why we just don't replace this one, which is a castor oil, which is non-degradable, by using like soybean oil, which could be degradable. Because the soybean oil need a lot of chemistry to convert it to OH group. But this one has already the OH group, which is ready for the chemistry. So here we have the OH group, which can react with the diisocyanate. And then we can get this network, this three-dimensional network structure. And after that, we neutralize the carboxylic acid by triethylamine to be able to disperse the material in water. And it has a very nanostructure. It's the diameter of the particle of the polyurethane is about 30 nanometer, which is very small. And by casting this dispersion, we have the water, which is the matrix, and the dispersed phase, which is the polyurethane. By casting this on any substrate, the water will evaporate it. Coalescence and interdiffusion of the particle also will take place. And then we have a very nice film. We will have this film on the surface of this pot. And this is why we have it a little bit shiny when you check. So you see it is a little bit bright color. And how we make the deep coating is we just dip it in the container, and we have a layer on the surface of the pot, and then we let it evaporate. We can control the thickness of the coating by controlling the concentration of the solid in water, or by controlling the viscosity of the material. We can calculate normally the thickness of the coating material using this equation. We can make also the coating several times. We make first dip, and then we let it to dry for a day or something, and then we can make another deep coating. So we can increase the thickness.
Spray it on them. You're going to dip, why don't you just spray it on?
It is more. This is more easier because we have a very homogeneous coating on the surface. We don't use the spray. We have the container here. Has a polyurethane dispersion, water base, and then we dip it and then we take it out and dry, let it dry. And then you can have a very thin, if you just let it dry for like a day under vacuum, you will have it very dry, very nice film on the surface of the pivots. The spray could also work, but we don't prefer that one because this one, it is very fast, and maybe we can control the thickness. Spray, it's also same things, but we prefer this.
All these cuttings were done on a really small scale in a pilot plant.
Well, that's what I'm asking.
A larger producer of these paper fiber containers might be able to do a spray.
The reason I'm asking is
what we've done
contamination of the main parent body is what you're wanting. Every time you're dipping in a pot, you're going to contaminate the main material. That's the only thing I'm concerned about in most cases.
Well, what I did was when I dip coated these, I took it from the main material into a smaller container and then dipped smaller amounts through that. So I never actually really contaminated the main stuff, but they did use a smaller one to do multiple coatings.
They had the same problem when they started using copper on the outside of the pots, how they started treating it in most cases here, and then they went to the incorporation later on.
But we haven't seen any toxic effect on the plant, because if it is contaminated with some undesirable stuff, maybe it will have some effect on the growth rate of the plant, but we haven't seen that. So it is, I think there is no any contamination. And this is the glass relaxation process of the solid film. So when we cast it, we do some dynamic mechanical thermal analysis. So the material has a glass relaxation process at about 40 degrees, and the TG here, it is about 20 degrees. So the material is very elastic. It's the extension is about few hundred times. It's very good material. And this is the water uptake. So we found that by making this deep coating to the surface of the pivot, the water uptake decreased dramatically. And we still have this data for the other coating like tung oil, polyamide, but this is in chloroform. Polyurethane, this is the material we have used. It is up here. So it decreased dramatically. So we can let the water uptake or the water sensitivity decrease significantly by this deep coating. And I think this is my last slides. And the main things here is the mechanical properties, degradation rate, and the production cost can be greatly controlled by blending and make a composite with some of the filler like DDGs, cornice-over, lignin. The water resistivity or the water uptake can be also decreased significantly by deep coating with polyurethane dispersion.